Welcome back to Mathematics Lifeline. Today, I'd like to explain to you what implicit differentiation is and how to solve it. So, implicit differentiation, what it is a way to solve a derivative when you have more than one variable in your function. So, if you have an x and a y in the same function, well, how do we take the derivative of that y term? That's what implicit differentiation is going to help us do. It's going to help us take the derivative of other variables besides x. So the notation that we've been used to is d dx, and that means the derivative with respect to x. We're used to that. What we need to learn is dy dx, and I'm going to say it like that. I'm not really going to say dy over dx because I think it's just faster to say dy dx. But that means the derivative of y with respect to x. So if we have a function that has y as a variable as well, we're going to need to put dy dx to specify what variable we're taking the derivative of. So you'll see that in this example right here. So let's say that we have the equation x cubed plus xy plus y cubed is equal to 1. So with implicit differentiation, what we have to do is we have to take the derivative of both sides of this equation. So we have to take the derivative of this whole part right here and take the derivative of 1. Well, you can see which one the easy side is going to be because we have the derivative of 1. Well, that's just a constant, so the derivative of 1 is just going to be equal to 0. So let me put that up here a little bit. It's going to be equal to 0. That's the derivative of 1. So now we have to take the derivative of this. So what we're solving for here is we're solving for dy dx. We're solving for dy dx. So we're looking, the only time we're going to need dy dx is when we're taking the derivative of these y terms. So when we're doing just normal x's, we're going to do those just as we've done this whole time. We're going to do them just as x terms. So these are just going to be, this is just going to be the power rule right here. So the derivative of that is just going to be 3x squared. Plus, now is where it gets a little different because we have an x times a y. So we know that anything multiplied by each other, when we're trying to find the derivative, we have to use the product rule. So we have x times y, so we're going to do that the same way that we would do any other product rule, but now we're going to add a dy dx, and you'll see where we do that. So again, with the product rule, we're going to do the first term, x, times the derivative of the second. Well, the derivative of y, I'd like to treat y like x at first. Because when you're confused with what the derivative of this is, well, imagine the derivative of x. The derivative of x is just going to be 1, so the derivative of y is going to be 1, but we have to multiply by dy dx. And the only reason we do that is because we took the derivative of it. So when you take a derivative of y, no matter what it is, if there's a y and you're taking a derivative, you have to put a dy dx. So that's the first step of the product rule. Now we have to add the second term, which is just y. Now notice I'm not putting a dy dx here because the dy dx is not needed. We're not taking the derivative of y. We're just writing y down because that's the product rule. So if you're not taking the derivative of it, you're not going to need it. But when you do take the derivative, you do need it. So now this is y times the derivative of x, which is going to be times 1, plus, well, now we have a y cubed. So again, treat this like an x cubed. We're going to use the power rule here. So it's going to end up being the same as this, but with a y. So it's going to be 3y squared. But remember, we took a derivative that had y in it, so we have to put a times dy dx. So now we have to simplify this. So this part right here is going to stay the same. We have 3x squared. Plus, well, when we multiply this out, we have x times dy dx. Plus just a regular y, because it's y times 1, so plus y. Plus 3y squared times dy dx is equal to 0. Okay, so now we've done most of the derivative work, so now we need to solve for our dy dx. So we need to get these dy dx's on their own. So the way to do that is we're going to move all the terms that don't have dy dx. So our 3x squared and our y, where they don't have, they're not multiplied by dy dx. So we're going to move those over to this side. So then we end up with x plus, or sorry, not x plus, x times dy dx plus 3y squared times dy dx is equal to negative 3x squared, because I subtracted this over here, and I'm subtracting the y, so minus y. Now what we have to do is we have a dy dx in both of these terms, so we can go ahead and factor that out. So let's say dy dx multiplied by what's left, so we have an x plus a 3y squared. That's equal to negative 3x squared minus y. So now we want this dy dx on its own. We see we're multiplying by this, so we're just going to need to divide by this now. So divide everything by x plus 3y squared. See that this cancels out with that. We end up with dy dx equals negative 3x squared minus y all over x plus 3y squared. That's going to be our derivative using implicit differentiation. So you can see with this that, you know, it is kind of long, it's kind of drawn out a little bit, it's a lot of steps, but it's all stuff that you know how to do. It's all stuff that we've done before. So there's nothing new. The only new part is knowing that when you take the derivative of y, no matter what it is, if you're taking the derivative of it, you have to put a dy dx. That way you can solve for it, because if you don't have any dy dx's here, well, you're never going to be able to solve for dy dx because you're solving for nothing, because it's not there. So we need to put the dy dx in. So let's do another example. Let's say that we have the equation x plus sine y is equal to xy. Okay, so remember that our first step of implicit differentiation is to take the derivative of both sides. This time we don't have a constant on the right side, so we can't put that equal to 0, but we do know how to take the derivative of everything in here. You see that this side is just taking the derivative of x and sine y. This side is the product rule that we did in the last question. So let's go ahead and take the derivative of both sides. So we know the derivative of x, that's easy. We know that's just 1. Plus, well, we have a sine y, so we know the derivative of sine is going to be cosine, so we're going to take the derivative of sine, and that's cosine, of y, but don't forget to multiply by your dy dx. You need that here. And that right there is your derivative of the left side. So now we set that equal to this product rule. We've done that. So we know that we're going to leave x alone, times 1, because that's the derivative of y, but don't forget your dy dx, times dy dx, plus y times 1. Remember that y is going to stay the same. It's not going to get multiplied by dy dx because we didn't take the derivative of it. We just left it alone. So now we have 1 plus cosine y times dy dx is equal to x times dy dx plus y. Now again, we're going to have to solve for our dy dx. So we need our dy dx on one side and everything that doesn't have dy dx on the other side. So I think the easiest way to do that is going to be to bring this x term over to this side and bring this 1 over here. So we're going to end up with cosine of y times dy dx minus x times dy dx. See, I just subtracted that over to this side. And that equals y minus 1. And this 1, I remember I subtracted over there. So now we have our dy dx's on one side. Remember, we can factor those out now. So now we have dy dx on the outside multiplied by what's left. So we have cosine y minus an x. Cosine y minus x is equal to y minus 1. Now, to get this dy dx on its own, we're going to divide everything by cosine y minus x. This cancels. This comes over here. So we end up with dy dx is equal to y minus 1 over cosine y minus x. That is our derivative. So, again, none of this is new. I think this example was actually a little easier than the last one because even though we had to move dy dx's around, it's the same concept and our answer is a lot more simple, I think. But, you know, I hope you're getting the hang of this. I hope you're getting the hang of when you take the derivative of y, you have to put a dy dx. As long as you understand that, there's nothing new except for factoring and dividing. But that's stuff that you already know how to do. If you're in calculus, you know how to factor. If you're in calculus, you know how to divide. So all we're doing is adding those steps in so we can solve for our dy dx. Remember, when we have something like this, we're solving for dy dx. So let's do another example here. Let's try x to the fourth plus y to the fourth is equal to 16. This example is incredibly easy, and calculus textbooks love this example. Don't know why they like it so much. It's really simple. I probably should have started with this one, honestly, because there's no product rule, there's no quotient rule, there's nothing at all new except for the dy dx. So let's think about what this is. We have to take the derivative of both sides. So we're going to start with this x term. That's going to be 4x cubed using the power rule. Plus, again, we're going to use the power rule here, but just multiply by dy dx. So this is 4y cubed times dy dx. And this is equal to the derivative of 16, and that's just going to be a 0. So now it's just about bringing this term over here and solving for your dy dx. So we're going to have 4y cubed times dy dx is equal to negative 4x cubed. And here we don't have a second term. We just have a 4y cubed. We're not adding anything. We're not subtracting anything. So we don't even need to factor this out because it already is. All we need to do now is just divide by a 4y cubed. So we're going to divide this side by 4y cubed and divide this side by 4y cubed. Those are going to cancel. Now we have dy dx is equal to negative 4x cubed over 4y cubed. The only other thing we can do here is take these 4's out. So we know that this is the same as negative x cubed over y cubed. And that right there is our answer. That example I think is so much easier than the other ones. But it really, all you need, and this proves it, all you need to know is that when you take a derivative of y, you put a dy dx, solve for that. That's all it is. So this derivative looks a little weird, but all we did was solve for dy dx. And when we do that, we get our answer. So what I haven't shown so far, what I've kind of left out, is that we've been doing dy dx this whole time. So let's say that we have this equation. Y is equal to x cubed plus 4x squared plus 7x plus 9. So we would know how to take the derivative of this. So we would just take the derivative of all these x terms. This would be 3x squared plus 8x plus 7. That would be our derivative. And when we would box it, we'd be perfectly fine. But now we know that we're really taking the derivative of both sides. So we're taking the derivative of this y, we're just not showing it. So the derivative of y, we remember, is just 1 times dy dx, or it's just dy dx. So every time you take a derivative of a function like this, so a lot of times I would put f of x. But f of x is the same thing as y. We know that those are kind of used interchangeably in a regular coordinate plane. So we're really taking the derivative of y this whole time. I'm just not writing it. So you see that dy dx isn't a new term, it's just a new notation. We've been using it, we just haven't been showing it. So it's going to help to know that, because if you know that the derivative of y is dy dx, you'll know to put that in all of your examples, and you'll know to multiply it by any derivative of y. When you have something like this, you don't need to put the dy dx, but that is what's really on this side. When I say, the reason why I haven't said it is because when I say to take the derivative with respect to x of this function, this isn't in the form of an equation, right? We don't have that equals y. It's kind of implied, but we don't have that equals y. So I can just say to take the derivative. But when I have y equals, we're solving for dy dx. So just remember that if you have a y, it's really dy dx. It's not always d dx. But yeah, that's going to be it for implicit differentiation. I like this lesson because I think it's just so similar to everything else. There's not a lot of new material. But yeah, if you do have any questions on it, as always, you can let me know in the comments. But if not, then I will see you in the next video.